In this video, we'll talk about another way to form enols. This is actually through a reaction that's covered in Organic Chemistry 1. So this is an addition reaction, and we're adding H2O. So H2O addition to an alkyne, so a molecule with a carbon-to-carbon triple bond. We'll show the reaction scheme here. So if we have carbon-to-carbon triple bond, we'll say one's bonded to a carbon chain, one carbon's bonded to a hydrogen. We add H2O and we have acid present. A hydrogen adds to one carbon and the OH group adds to another. And so the product of this, we'll show the mechanism, but just to draw the product here, the OH group adds to the more substituted carbon and the hydrogen adds to the less substituted carbon. So this is an enol, and when this is covered, if you were in my class in Organic Chemistry 1, we ended the class here. So we said this forms an enol molecule, carbon-to-carbon double bond with an OH group. But in reality, this enol, just like we saw in the last video, rapidly interconverts with its ketone form. So that would be, now we have a CH3 group bonded to that carbon in the center, and the carbon is double bonded to an oxygen, and here we have a ketone. So let's go through the mechanism here. To show how this is formed, we covered the mechanism. So we're showing the mechanism to form the enol. This is the addition reaction mechanism that is covered in Organic 1. So we have an electron-rich triple bond, and we have an acid present. So if we have water and acid, that means present in solution is H3O+. Electrons in the triple bond grab a proton, and so that forms now an open shell carbon. So the less substituted carbon is the carbon that gains the new hydrogen. So that means our more substituted carbon is a carbocation. This was Markovnikov's rule, you might remember. And then now water will add to that carbonyl carbon, and then we will deprotonate. So we can deprotonate with neutral water. And this forms that enol product there. Okay, so that's the mechanism to form the enol, but let's see how, once we form the enol, then how are we getting to the ketone? So we'll start with the enol now. Okay, just copy down the enol here. We're in acidic solution. We're in acidic solution. So we have, let's say, hydronium. Right, we're still in the same solution as what formed the enol initially with that alkyne. The double bond now, just like in the first mechanism, the double bond will grab a proton. And so the less substituted carbon is what will be bonded to the proton, the new proton. We have a single bond here. Now we have 3 hydrogens. So CH3 group. We have our OH group, and this is another carbocation. This is an equilibrium reaction. So we formed the carbocation intermediate. Hopefully you can see this is a resonance stabilized carbocation. So we will show resonance here. Oxygen electrons can create a double bond between the open shell carbon and itself. Now I'm going to simplify this CH3 group as just a CH3. We have a carbon double bonded to oxygen. Oxygen is positively charged. So this is resonance here, resonance stabilized. Carbocation. And now the second structure that we've drawn, well, the third in green, looks just like a protonated ketone. And so neutral water, still present in solution, can deprotonate that carbonyl oxygen, and now we've formed the ketone. So this is how, in acidic solution, how an enol would be converted into a ketone. And so enols and ketones rapidly interconvert in general. So enols and ketones, we have rapid interconversion. So let's define, we said in the last video that enols and ketones are tautomers. Let's define what that means. So enols and ketones are tautomers. So this means they are molecules that are readily interconvertible constitutional isomers. So readily interconvertible constitutional isomers, remember constitutional isomers have the same formula, same number of each type of atom, but different connectivity. So if you have constitutional isomers that exist in equilibrium with each other, like enols and ketones, they're tautomers. So they are readily interconvertible constitutional isomers that exist in equilibrium with each other. So at equilibrium, the percent of enol present so whether reaction, the equilibrium lies to the ketone side or the enol side, and to what degree it would lie to either side, this depends on multiple factors. Some are the structure of the compound, the solvent can play a role. So there are multiple factors So far for us, we just need to know that both enols and ketones are present in equilibrium with each other.